Hey everyone. So I'm going to try my best to do today's notes. My expectation is that you take your notes and let me turn up the volume, that you show me your notes tomorrow in our next class. So our learning goal for today, limits involving infinity. The learning target is I can determine limits of infinity. And I'm going to kind of go over some examples. I'm going to try to use these Zoom annotation tools to see if I remember it to the best of my ability. So let's try this, y'all. Let me start my slideshow. And again, forgive me for any errors. I am doing this like in the moment. So yes, so definitions. First things first. So limits involving infinity have the notation like so. Limit as x approaches infinity of some function f of x. And again, it's what I just said verbally is written down here. So again, what that means is that the limit as x moves increasingly to the right of the number line as you're looking on the coordinate plane. Limits involving infinity can also have this type of notation where your function, your x value is approaching negative infinity and you're trying to figure out what your function is doing near that location, AKA that means when the limit as x moves increasingly to the left on the number line as you look on the x-axis, so to the left when you're looking at a coordinate plane and a graph. So these are some of the basic definitions. And again, pause the video, to make sure that you get all the stuff down. This is an example of a function. This is the basic rational function graph, f of x equals 1 over x. And let's go ahead and determine the limit as x approaches infinity. That means what y value is our function approaching as I move increasingly to the right in my graph. That's what this is asking. As you can see, there is a horizontal asymptote happening. It looks like our function is approaching the y value of 0. Notice how for a limit, it doesn't have to actually touch 0 as long as it's actually approaching 0. So in effect, and you could also do this in the left-hand side, right? So the limit as x approaches infinity from the going towards the left on the number line on the x-axis. So again, the limit as x approaches in negative infinity on this location, your y value is still also approaching 0. So both of these, the answer would be 0. And ultimately, we use infinite limits to determine the end behavior of a graph. So how is the function behaving at the end behavior? And also, it helps us determine any horizontal asymptotes of a function as well. So for those of you who took pre-calculus or algebra 2 last year, we were able to determine some horizontal asymptotes with long division, polynomial long division, if you remember. Now we have a new tool in our bucket, limits, that can help us determine end behavior. So again, the answer, let me write it down, sorry. 0 and 0. Again, remember, these are what y value is my function approaching as it moves increasingly to the right on the number line and increasingly to the left on the number line. And when I say number line, I'm talking about the x-axis. Let me go ahead and clear my screen. All right, next slide. All right, so this is a formal textbook definition of the what I was just talking about. So let's write this down. So if x approaches infinity of f of x equals L, or the limit as x approaches infinity of f of x equals L, we say, and I'm like curious if this is missing a negative infinity. It probably is, because yeah, there's no difference between these two notations. So make sure one of these is negative, please. We say that y equals L is the horizontal asymptote of f. So that's a formal definition. Let me go ahead and adjust what I just said. One of these should have a negative infinity. So it's interesting. So again, according to the definition, since the limit from the going to the negative infinity this way is equal to the limit going to the right, positive infinity, we say that we have a horizontal asymptote at y equals 0. So that's just a basic application on using infinite limits to show that we have a horizontal asymptote. So that's just a little bit of a closer on that. Okay, y'all. Let me talk about this important term that you want to make sure gets down in your notes. And also, please jot down any questions that you want to ask me for in our next class. The principle of dominance. So it's an interesting principle. So this is super key to know. The limit as x approaches infinity of 1 over x is equal to 0. Let's go ahead and talk about this. By the way, this principle of dominance is also true if this was a negative or positive infinity. So negative or also positive. So it's also true for either. Why? So first off, we saw that this is true from the graph. We just looked at the rational function graph and we knew that this was true. So there's that. However, there's also a way to reason this, like by just thinking about numbers. So let's read what we have down here. This limit makes sense because the 1 in the numerator always remains the same, right? So we have 1 over x. The thing that's changing is the x in the denominator position right here, right? If x is going to infinity, the denominator is becoming larger and larger as x approaches either infinity or also negative infinity. So what happens when you take 1 and you keep dividing by a larger number? Your whole fraction is going to approach 0. So that's how we could kind of reason why this limit is true as well. So for example, if you do 1 divided by a billion, you're going to get 0.0, a very small number. So that's why it's the limit of this is equal to 0 because your function is approaching 0. Remember, limit means approaching, the function does not have to actually equal 0. So again, we notice we can find this limit since x gets larger where our numerator remains constant, the same. And we could apply this same idea, the principle of dominance, to these examples that y'all are going to write down. Again, please pause the video to get all of this down. You're going to show me your notes in our next class, and it will be for credit. Okay, next. Let's go ahead and do some examples together, y'all. So all of these apply the same reasoning that I just described. Notice how, for the most part, example 1 and example 3, they have a constant, a number in the numerator position, and they have a variable in the denominator position. The same idea applies that as x gets larger and larger in the denominator position and my numerator remains constant, sooner or later, your function, your overall function will be approaching 0. So to apply the principle of dominance here, the limit of the first one is 0, limit of the third one is 0. What about this one? Why did I skip this one? So I skipped it temporarily because we don't have a numerator in the, we have a numerator. We don't have a number in the numerator position. However, if we simplify this expression, we can have a number. So take a look, let us perform some magic. So limit as x approaches, see, it's been a while, y'all. Anyways, so x squared is the same thing as writing x times x. And then x to the third is the same thing as writing x times x times x. And let's go ahead and simplify. So that goes away, that goes away. Remember that when you cancel all of the stuff out from the top, there's still an imaginary 1 at the very top. So what we have is a limit as x approaches infinity of 1 over x. Well, lo and behold, y'all, this is the principle of dominance precisely. The answer to this is 0. So that's nice applications of the principle of dominance. However, there is more applications, more complicated functions. Let's check those out. Let me clear my screen. And again, copy this down, pause the video. It's for the sake of making this video not too long. So I'm just going to move ahead. Okay, let's go ahead and extend the principle of dominance, everyone. Let's find the limit of this particular function. So I'm going to show you a strategy that we can use. And let me use a different color. My goodness. Okay, let's do this. So the limit as x approaches infinity of this over that. So one thing I want you to notice, there's a 2x in the numerator position. There's a whole quadratic function in the denominator position. Here's a strategy that I'm going to share with you. We're going to divide the top and bottom of this fraction by the largest degreed term in this expression. Let me show you what happens when we do that. You'll see how we can apply the principle of dominance. So let's do it. So I'm dividing, so the first off, the largest termed value in this whole expression is this one. So largest degree term. So degree means exponent. This is the largest exponent found in our expression. So that's step one. You identify that. Now we're going to divide top and bottom. So that's a division. We're going to divide top and bottom of this expression by x squared. So divide by x squared. So then in my next step, which will take me a bit to write, and again, feel free if you need to flash forward in the video, looks like this. So it's going to be 2x over x squared, that's the top, all over x squared plus 3x plus 2. And that's also all over x squared. So we got to divide the whole thing by that largest degree term. So that's what we have thus far, right? We're not going to be doing flip and multiply, actually. This is what we're going to be doing next. So for this bottom thing, I'm going to rewrite this. So take a look at how it's called the splitting your fraction. And we could do this. This is allowed. Take a look. So I'm just rewriting my numerator just for the sake of showing you very clear steps. So this bottom part, I'm going to split the fraction like so. We're going to have x squared divided by x squared plus 3x divided by x squared plus 2 all over x squared. So this is the expression we have. Great. Now, the goal here and why this method is going to be nice is because we're going to try to make each term look like the principle of dominance so that we can apply the principle of dominance. Again, you use this principle whenever we have infinite limit like such, or we call them limits of infinity. Okay, so what we're going to do is I'm going to now go and simplify each term here. So then 2x over x squared, we could cancel out an x from the top and bottom to become equal sign. That's going to become 2 over x in the numerator position. All over, let's simplify each of these now. So x squared divided by x squared. Anything divided by itself is 1 plus 3x over x squared, middle term. That will simplify if you cancel out an x from the top and bottom into 3 over x. And nothing can happen here. Nothing I could do to simplify that. So now I have this. Nice. So this looks really gorgeous. I'm going to have limit as x approaches infinity right here. Great. So basically, we're going to apply now. We can apply the principle of dominance. So for example, this one, we know that as x approaches infinity, that's going to approach 0. Nice. When this expression approaches, and when the x value approaches infinity, the whole function here will approach 0. When this whole function, when this x value approaches infinity, this whole function or expression itself will approach 0. This is the only thing that won't approach 0. So, okay, we'll just leave that there. So essentially what this becomes is equals the limit as x approaches infinity of 0, top is 0, 1 plus, we have 0 plus 0. So then that becomes the limit as x approaches infinity of 0 over 1, which is basically 0, right? So I'm just going to write 0 divided by 1 is 0. You can check your calculator. So limit as x approaches 0, limit as x approaches infinity of 0 of a constant is just the constant. So the limit of this whole expression, y'all, is 0. And this is how we apply the principle of dominance. So notice we had to use like an algebraic technique of dividing the top and bottom of the fractional expression with the largest degree term. And then we were able to apply the principle of dominance to each term to arrive at a solution. So again, please make sure you pause this video and get these full steps down. I am looking for the full steps. And then later on, I'm going to share with you some patterns we could find so that we could quicken our process. So let me clear my screen. All right. And, oh, by the way, whoops. So the answer was 0. And I also took the time, I put this function on Desmos. And as you can see, as x approaches infinity, both towards positive infinity and also to the left, but this is only asking about positive infinity, so I'm just concerned about going towards the very right. Notice how it is indeed true that the function, as it moves increasingly to the right, is indeed approaching the y value of 0. So it's pretty cool. Like, it's a funky looking graph, and we're able to determine that horizontal asymptote. Very, very cool. Okay, next, let's take a look at this type of function. Now, I purposely chose this one because we're going to get something other than 0, actually. I know you're probably thinking all of these have an answer of 0, but no, not true. All right, y'all. Step 1, identify. We're going to do the same steps. Step 1, identify the largest degree term. And it looks like here that the largest degree exponent is going to be x to the 3rd power. Now, we're not going to take that whole term. I'm just going to be concerned about, the variable with the highest term. So we don't have to divide the whole thing by 5. You could have also chose this one. Either way, it doesn't matter. So I've identified the largest degree term. I'm only concerned about the term that has just a variable in it. And again, we're going to repeat our steps. We're going to divide top and bottom of this expression by x to the 3rd. And then that's going to become 2x to the 3rd divided by x to the 3rd minus x squared all over x to the 3rd plus 8x divided by x to the 3rd. Let me undo. Big old fraction bar. So that's the top, right? Let's go ahead and take care of the bottom. We have -5. Oh gosh. Anyways, -5 x to the 3rd divided by x to the 3rd. Then we have plus 7 all over x to the 3rd. And again, I like to be consistent that I'm saying this is equal to the limit of, as x approaches infinity. Okay, now we're going to go ahead and do the same thing we did before. I'm going to go and make sure I simplify each and every little fraction I see here and then apply the principle of dominance. So let's do that. So this is equivalent to the limit as x approaches infinity of, now this first term will simplify to just 2 minus this second one will simplify to 1 over x Again, you want to just write it out if you have any questions. This third term is going to simplify to plus 8 over x squared. All over negative 5x to the third divided by 5x to the third. All those x's will cancel out. You're just going to be left over with negative 5 plus, and it looks like nothing cancels out from this. So, woohoo, now we could apply the principle of dominance to where we can. This one, as x gets bigger and bigger, will approach 0. This one, as x gets bigger and bigger, will approach 0. This one, again, as x gets bigger and bigger, will approach 0. Now then, quite a workout. What we're left over with in this scenario, limit as x approaches infinity of 2 over negative 5, because the rest of the stuff became 0, right? I'm not going to write that. And the limit of a constant, y'all, is always the constant. So it's negative 2. That's a 5, by the way, over 5. Remember, if the 5 is negative, that just makes my overall fraction negative. That's why I moved the negative in the front. That is the limit. And this is using the principle of dominance. Pretty cool. Let's see. Oh, great. Look, y'all, I have a graph. So it's really cool. We could have totally used long division to see what the horizontal asymptote is, but now we're using calculus, y'all. Take a look. As x goes increasingly to the right on the lumber line, right? Like here, notice how the function, I know it's hard to see, but if we were on Desmos and you were to zoom in, the function, the y value, as x moves increasingly to the right, will approach the y value of negative 2 over 5th. Notice that. It's kind of cool. It's really awesome. It's a nice application. Less work than long division too. I mean, if you know the principle of dominance and you apply it. So there's one more case to talk about, and it's an interesting one. Let me clear my screen. Oh, let's just go. There we go. So, y'all. Oh my goodness, I don't like that. I put a table thing here. So give me one sec. Take that out and put that here. We'll talk about the table, and I don't want to explain this rule just yet. So delete. I mean, if you want to, have a peek, go ahead. I'm like, hey, what happened to the graph? Okay, whatever. I want us to look at this graph, so maybe I'll just go on Desmos right now. But okay, everyone. So this is example 3. Sorry, it doesn't have my goodness gracious. Okay, it doesn't have a title, right? This is example 3 in your notes. And I specifically chose this for a particular reason that you'll see in a second. And then I'll go over those shortcut rules that you just saw, so don't worry. All right, so again, we're going to do the same thing. Identify the highest degreed expression or term. And I notice it's x to the third. Great. So we're going to divide top and bottom by x to the third power in this case. And we're going to try to apply the principle of dominance. So let's do this. Great. Once we do that, we have, if we were to write it all out, 4x to the third power divided by x to the third power minus 2x squared divided by x to the third power plus 8x divided by x to the third power all over 3x squared divided by x to the third power plus 3 all over x cubed. And again, this is the limit as x approaches infinity. Ooh. Okay, so now we're going to do as typical. We're going to just go back and try to reduce each fraction. Over here, x to the thirds will cancel out. We just get 4. We're going to get 2 over x over here. Then we're going to get plus 8 over x squared all over 3 over x. And then that last one doesn't simplify. 3 over x cubed. All right, so now we're going to go in and apply the principle of dominance because this is a limit to infinity. So of course, let's go ahead and tackle this. So this, as x gets large, goes to 0. This whole expression, this as x gets large goes to 0. This one as x gets large goes to 0. And then this one as x gets large also goes to 0. So then let's go ahead and write this. So this is now going to become the limit as x approaches infinity of 4 all over 0. Now, what does that equal? So we applied the principle of dominance. We followed all the steps, but we can't divide by 0. So there's a problem. The principle of dominance was unable to help us here. So to determine this limit. So what's going on here? So there are different ways to determine the limit, y'all. One way would be to graph this and see what the limit is as x goes to infinity. Another one is to make a table. Let's go ahead on Desmos and see what in the world this limit is. So let me escape from here. And I'm going to go to desmos.com. And again, I'm going to have to type in this whole function, but it's going to take me a bit. Oh, goodness gracious. It's 4x cubed. I don't have a good memory, minus 2x squared. And then we have plus 8x. No. Plus 8x. That's all going to be divided by 3x squared plus 3. 3x squared plus 3. Now let me clear my screen so we can see what's going on here. Whew. Okay. So then as x goes increasingly to the right, because we're trying to figure out what happens as x goes to positive infinity. Let me just zoom out. What in the world's happening? Like it looks like it's becoming something like linear, right? At its end behavior. And as x goes more and more to the right, it looks like this function is going more and more towards positive infinity. So this function itself is not really approaching a value. This function is just growing larger and larger in its y value as x grows larger and larger in its x value. So the answer to this limit is infinity. The limit as x approaches infinity of this expression is infinity. Now, what's interesting about this function, if you recall, if we were to use long division, you would get that there is a slant asymptote here. And there's a slant one. So this one does not have a horizontal asymptote. It has a slant. It's going to be some linear function. That's what we call a slant asymptote that approximates the end behavior of this function. So it's pretty cool. So great, y'all. We have an answer. This one will be infinity. And then maybe you're thinking like, goodness gracious, I don't want to be graphing functions to figure out the limit. It does take a lot of work. So again, we could make a table. So you can make a table and notice in this table how I chose values that x values that just get larger and larger and larger. I mean, you could immediately just jump over to a very large number and just see what's happening. Notice that the y value just gets bigger and bigger. Let me go ahead and show you some rules. Now, there are shortcut rules. However, there will be instances in the quiz, in our next quiz, where I asked you to formally show and prove the way I showed you, applying the principle of dominance with full steps on how to get a limit answer. But here is actually the shortcuts, y'all. Please write this in your notes and pause this video. So basically, I don't know if you've noticed yet or not, but here it says, if you have an expression, if the top exponent in your rational expression is less than the exponent in the largest exponent in the denominator position, then the limit of the expression is 0. So again, this makes sense because the denominator will be growing faster than the numerator, and overall the whole expression will equal 0. Now then, if you have it such that you have some rational expression like so, and now if the largest degree powers of x are equal, then the limit will actually be if you take c over d, whatever those constants are, whatever the numbers are in front of them. And again, if you go back to the example in a second, I'll show you this version. Now, the third case happens when the degree in your numerator is larger than the degree in the denominator. That was the example we just saw. If that happens, then actually your limit is either going to be positive infinity or negative infinity. All you got to do is, again, look for the highest degree powers. But how do we know if it's a positive or negative infinity answer without making a table or graph? What you do is just go ahead and substitute a very large value for x. Try x equals 1,000. See if your answer is positive or negative. That's going to let you know whether it's positive or negative infinity. Pretty cool. So let me go ahead and escape from my screen. And let me walk us through back to our example. So this, in example 4, notice that the largest degree term is in the denominator position. That's the first rule where the limit, right, would equal 0 because the degree in the denominator position is larger than the degree in the numerator position. Now, for the second case, that's example 5. Notice how the largest degree term was the same in the numerator and denominator position, x to the third power. And the answer for example 5 was -2/5. You just take the fraction of the constants that are in front of the largest degree terms. Pretty cool. And then of course, our most recent example, notice how the exponent, the largest degree exponent was in the numerator position. That's when you got to actually test it out by choosing large values of x, substituting, and seeing whether your answer is positive or negative. Again, here are the rules, and those were the different examples that kind of highlighted the rules. So again, please make sure you get them down. And pause the video and get these down. And then we'll move on to our next thing. So that's the principle of dominance. Thank you all so much. And looking forward to checking in about this. Bye, everyone.